Hello, in this video I'd like to put together this kit here. This is the Hyperdo kit from Zometool. And what it is a three-dimensional projection of a four-dimensional platonic solid called the 120 cell. And what does that mean? What does it mean to be a platonic solid in four dimensions? Well, I'd like to get started by talking about what it means to be a platonic solid in three dimensions. So here I have all five platonic solids in three dimensions. And the key thing here is that every face is going to be a regular polygon, right? So kind of the platonic solids of two dimensions. And then more than that, these shapes have to be highly regular. And what that means is that if I have a face, I can change the orientation of the face. I can rotate that face however I want, and the appearance of the cube remains the same, right? So I don't have something sticking off that will rotate along with the thing and give a different appearance when I rotate that particular face. So I can rotate every face however I want, and the appearance of the cube stays the same. And I can also take, if I have two faces, I can rotate one face into the position of another face, and again, the appearance of the cube will stay the same. And so what this means is that these things are full of symmetries. There are lots of different ways of rotating a cube that will keep it looking the same after we've done that rotation. And that's what it means for something to be a symmetry. So here, the cube is constructed by taking regular fourgons, right, regular squares, and combining 3 at every one vertex. And that's enough to construct a cube if you do that. We also have the dodecahedron, which is we take 12 pentagons, regular pentagons, and we join them together so that at every vertex we have 3 pentagons meeting, and that's enough to determine this shape here. Again, it's highly regular. We can take these pentagons and rotate them however we want, and the overall shape of the dodecahedron stays the same. And we can also take one pentagon and rotate it into the position of another pentagon, and again, the overall appearance of the dodecahedron stays the same. We also have the tetrahedron, the four-sided platonic solid, where every side is a regular triangle, and we have 3 of them meeting at every point. We have the octahedron. This is 8 regular triangles with 4 triangles meeting at every point. And here we have the icosahedron, which is 20 regular triangles with 5 triangles meeting at every point. And so if we wanted to create one of these, all we would have to do is create a whole bunch of, let's say we wanted to create a dodecahedron, we just create a whole bunch of pentagons and we would fold them up into the 3rd dimension in order to, and to get them all to meet with 3 pentagons per every vertex, and get the whole thing to close up. And what we can do is we can actually do the same thing in 4 dimensions. We can take a bunch of dodecahedra. So in particular, this here, we take 120. That's why we call it the 120 cell. We have 120 dodecahedra. And these are, we can have these in 3 dimensions, and then we can fold them up into the 4th dimension so that 3 dodecahedra meet around every edge, and the whole thing closes up and it creates this highly regular 4-dimensional platonic solid. Of course, the issue is that we don't live in 4-dimensional space. It doesn't really make sense to talk about having a 4-dimensional object. So how can we take a 4-dimensional object and bring it into 3 dimensions? Well, the same way that this video camera is taking 3-dimensional objects and bringing them to you in 2 dimensions, we're going to use projections. And actually, it's a little bit different from the way that the camera works. The camera is doing projections from a single point, but what I actually want to do is take projections that just kind of squish everything flat as opposed to squishing everything downwards towards a point. And it makes the math a lot easier. Essentially what we're doing is we're taking the four-dimensional points that make this up, and we're just ignoring their last coordinate, and that's going to get rid of that. Usually we call it the W coordinate. We have X, Y, Z, and then W because we've ran out of letters coordinates, and we ignore the W coordinate, and that's just going to give us X, Y, and Z coordinates. But ultimately, it's the same sort of process as how a camera works or how shadows work. Particularly, it's how shadows work if the light source is infinitely far away. So again, you don't get that kind of projecting down into a point or around a point. We're just trying to project a whole bunch of layers flat into 3 dimensions. And so again, this is the shape that we have. In this video, I will be building these out of Zometool. So what is Zometool? Well, Zometool is this very clever building toy you can buy. It's a little bit expensive, but well worth it. It has a bunch of these little white balls that have a whole bunch of holes in them. And what I've done, actually, so that you can see these a little bit better, is I've created a larger version of the Zometool ball out of Zometool. So this here is a model of the Zometool ball, and we can see the sorts of holes that it has. One of the holes that it has is a pentagonal hole. Into these holes, we have red pieces that fit. We have rectangular holes like this here. And into those holes, blue pieces fit. And then we have triangular holes, this here, and into those holes, yellow pieces fit. And because of its nice symmetry, these kind of combine the symmetries of a dodecahedron and an icosahedron, and that allows us to produce a whole bunch of different types of symmetries and a whole bunch of different types of shapes, including all of the platonic solids. So here I have a tetrahedron made out of, you actually have to add in a new piece that's a little bit bent. I don't know if you can see this even, but it's a little bit bent. These are the green pieces, and they also fit into the pentagonal holes. But it allows you to build tetrahedra, allows you to build cubes, allows you to build octahedra, allows you to build dodecahedra, and then to get up for this. And it allows you to build icosahedra. So you can build all of the platonic solids and all sorts of other things out of Zometool. So let's put this together. Our first step is going to be to build a dodecahedron. So this dodecahedron is going to be the center dodecahedron of our construction. And what's going to happen if we imagine we're taking a projection of our 120 cell into 3 dimensions. If we imagine, so as you can see, projected by the camera, we have a projection of this dodecahedron into 2 dimensions, right, from 3 to 2 dimensions. And one of the things that you can see is that we have a pentagonal face that directly faces the camera, and that pentagonal face isn't going to be distorted. On the other hand, these other pentagonal faces around it are distorted by the camera, right? This pentagon here, even though it is a regular pentagon in three-dimensional space, doesn't appear to be. It's been squished down in this direction by the projection of the camera. And so the same thing, this dodecahedron is going to be kind of the central dodecahedron. It's the one that's quote unquote facing the camera when we do our projection. And so it's not going to be distorted, but the dodecahedra around it are going to be distorted. So let's start putting those dodecahedra together. And so here we have a dodecahedron, and this is, well, this dodecahedron has been squished in this direction. And what that actually represents is that it has been folded up into the fourth dimension. That the actual dodecahedron in the actual 120 cell in 4 dimensions has been folded up into the fourth dimension. But because we're not drawing that direction, we're not drawing this extra fourth dimension, we're only getting one. So we have the actual length, and then we have the length in the fourth dimension, and then we have the length in 3 dimensions, forming a right triangle. And so we're only getting the base of that right triangle, even though the hypotenuse of that right triangle makes this dodecahedron the same size in 4 dimensions as this dodecahedron, right? So we're missing out on some of its length in this direction because that length is going into the fourth dimension, and we're ignoring that that fourth dimensional length. So this is these are the dodecahedra that are going to go in what I'm going to call layer 1. Right, so this is layer 0, this is the central dodecahedron, and then we're going to take 12 of these, they call them fat red cells because they have been squished in a direction indicated by the red connectors. And we're going to take 12 of these and stick them on to all of the faces of this original dodecahedron. There's just one slight issue. There are already pieces here. There's some overlap in pieces, and so we're actually going to have to remove a few pieces in order to get these two faces to be able to connect. So let's do that. So here we have the two connected onto each other, and then we're going to want to continue building these layer 1 dodecahedra around all of the faces of the layer 0 dodecahedron. So let me build another one of those. And again, there's going to be some overlap between adjacent dodecahedra. So and here we can see, just as a dodecahedron is 12 pentagons, where every pentagon, where 3 pentagons meet at every vertex, the 120 cell is 120 dodecahedra, where 3 dodecahedra meet at a particular edge. So these 3 dodecahedra meet at this edge here. And again, we need to fold up into the fourth dimension in order to in order to be able to accommodate that. Just like when we're putting together the dodecahedron, we need to fold up into the 3rd dimension in order to accommodate 3 pentagons per vertex. So I'm actually going to just build a whole bunch of these in bulk. So here I've finished a bunch of these dodecahedra, and it's a little bit difficult to see what's going on, but they're they're starting to engulf the central dodecahedron. So this here is 12 dodecahedra surrounding our central dodecahedra, and each of these dodecahedra has been squished in towards the center, just as you'd expect when we were doing projections in the three getting projected to two-dimensional case. All of these dodecahedra have been squished in towards the center because they're actually being folded up into the fourth dimension, and we just can't see that extra bit of length coming out of going into the fourth dimension. So this is what that looks like. And then for layer 2, remember that we're starting counting at 0, so the central dodecahedron is layer 0. These dodecahedra were layer 1. For layer 2, we're going to build dodecahedra that look like this. So here we have a dodecahedron that's been squished down in a slightly different direction, going this way. This direction corresponds to the yellow connectors, and so these are called yellow cells. And we're going to want to build 20 of them, and again, there's going to be a bunch of overlap between what we're trying to add on and what has already been built. So if we're careful, that can save us a lot of building time, and if we're not careful, it can increase the building time by quite a lot. So here we have two of the layer 2 dodecahedra, and again, I'm just going to automate this build process to make it faster. So that's layer 2 complete. We're almost finished, actually. The next step is to build on layer 3. And let me actually take this apart for a moment so I can show you what the dodecahedra of layer 3 look like. So here we have a dodecahedron that's been squished really flat in this direction. That's why they're called the thin red cells. This direction is the direction of the red connectors, and it's been squished thinner than the cells in layer 1. So this is the thin red cell. We're going to want to build 12 of these and connect them on. Again, I'm going to want to be a little bit efficient, so I'm actually going to build them all at the same time. And there we go. That completes the Hyperdo build. So we can see there are a number of directions that give us a bunch of nice symmetries when we look at them. Now hold on. We have one dodecahedron in layer 0. We have 12 dodecahedra in layer 1. We have 20 dodecahedra in layer 2. We have 12 dodecahedra in layer 3. That's 45 dodecahedra. Where are the rest of the dodecahedra? I was promised 120. Well, let me explain where they are. So first, there are actually 30 dodecahedra that we've already put together just as part of as part of the build process. And let me show you one of them. So this here is one of they call them flat blue cells because they have been squished completely flat in the blue direction. But nonetheless, they are dodecahedra. It's a bit like how if you have a 2D object and you look at it from the side, it loses a dimension. Similarly, we're taking this dodecahedra and we're looking at it from the side in 4 dimensions, and that's going to squish it down from the 3-dimensional dodecahedron into a 2-dimensional dodecahedron. And this is in fact what you get if you squish down a dodecahedron. Let me show you on another dodecahedron. So here I have another dodecahedron, and if I can line this up, it's not perfect because of the projection with the camera, but you can see, there we go, that these two look the same. And if I could get this much further away, they'd look exactly the same. This pentagon in the front and this pentagon in the back would completely overlap perfectly in the image that you were looking at. And we see that here. We see this pentagon here corresponds to those two pentagons. So this here is a projection that's gotten squished completely flat. It's a bit like how if we were looking at this dodecahedron from this direction, this face, even though in 3 dimensions it's a full pentagon, from your perspective it only looks like a line because of the way that the projection has happened. So that's what's happened with these flat blue cells. There's 30 of them. So that makes 75. Where are the rest? So just as how when we take the projection of the dodecahedron from 3 dimensions to 2 dimensions, right, via the camera, we have 2 pentagons that wind up getting projected down in the camera to this essentially the same pentagon. And again, if we weren't doing a point projection, if we were doing kind of a plane projection, these two would wind up being mapped to the same pentagon. We have a whole bunch of dodecahedra that actually are the projections of 2 separate dodecahedra, one on the quote-unquote top of the 120 cell and one on the quote-unquote bottom of the 120 cell. So actually all of the dodecahedra from layers 0, so the center dodecahedron, layer 1, layer 2, and layer 3 are all actually the projection of 2 separate dodecahedra in the 120 cell, right? We have the top, we have the bottom, and when we project them, the dodecahedra in the top and the dodecahedra in the bottom wind up getting projected to the same thing. So this, for instance, the dodecahedron in the exact center of this thing is the projection of both the very topmost dodecahedron and the very bottommost dodecahedron when they get projected from 4 dimensions down to 3 dimensions. And then the 30 dodecahedra on the faces of this thing are actually kind of the equator of this, right? We have the top, we have the bottom, and then we have this equator, and the equator is made up out of these 30, well, it's easier to think about in the case where we're projecting from 3 dimensions down to 2 dimensions. The equator is just going to be a circle that's kind of the outer edge of the projection. In this case, the equator is actually the sphere that's the outer edge of this projection. But anyway, those 30 dodecahedra, the flat blue cells, are only the images of one dodecahedron. It's gotten squished flat, so kind of the outside half and the inside half of the dodecahedra get squished together. But all of those, so those are 30, and then we have the 45 that I actually built, and then the copy of the 45. So let's say I built the top half, and then the copy of the 45 from the bottom half, and together that makes the 120 cells, 120 dodecahedra that make up this particular shape. So it is in fact the projection of the 120 cell. So let's talk about some of the patterns that you might notice looking at this particular construction. So one of them is this tunnel that runs through the entire model. It is 5 dodecahedra in a row where the top of one dodecahedron is the bottom of the other. And in fact, it's even better than that if you look at the actual 120 cell, because each of these 5 dodecahedra happens to be the image of 2 dodecahedra, one from the top of the 120 cell and one from the bottom of the 120 cell. Remember that each dodecahedron here is the image of two separate dodecahedra. And so, for instance, this pentagonal face here winds up belonging to two dodecahedra in the 120 cell. They just wind up both getting mapped to this particular dodecahedron here. And so if you actually look at this in the 120 cell, what we have are 10 dodecahedra in a row, where the top of one is the bottom of the other, and these kind of wrap around the 120 cell. In the same way that with a cube, you have a bunch of squares where the top of one square is the bottom of the next square, and they wrap around the cube. You get the same sort of thing here, and of course that happens in all sorts of configurations due to the regularity of this shape. So another pattern that you might notice is these bands. So here we have a vertical band and here we have a horizontal band where there are no Zometool balls. And this is actually an instance of a much more interesting property. You can see, so there's actually another band up here and a band over here, and they form a square, although it's a little bit difficult to see that square due to the fact that the camera that I'm using projects everything towards a point. It's easier to see in the 3D model where everything's being projected flat. But anyway, this is actually an instance of a much more interesting property, which is if we set our axes correctly. So if this is the x-axis and this is the y-axis, then we have the z-axis and of course the w-axis when we're talking about the 120 cell in 4 dimensions. So there are 600 vertices. In the Hyperdo model, there are only 330 Zometool balls because many of the vertices wind up overlapping with each other. But in the 120 cell, there are actually 600 vertices, and the x, y, z, and w coordinates of all of those vertices actually fall into a very small collection of possible numbers. It turns out that there are only 15 possible values for these different coordinates. And they are, so there's 0, so that corresponds to the 0 on the x-axis. And then we have 2 minus phi, where phi is the golden ratio, so that's about 0.382, and that corresponds to this value here. We have phi minus 1, which is 0.618, which corresponds to this value here. We have 1, which corresponds to this value here. And then we have our gap. We have our jump going from 1 to phi, going from 1 to 1.618. That's a pretty big jump relative to all of these other jumps that we're seeing. So that's why we see this particular band here. And then going from phi, we then go to 2, which is a bit less of a jump. And then from 2, we go to 2 phi minus 1, which is about 2.236, or the square root of 5. And then finally we jump to phi plus 1, which is about 2.618. So these are the different possible coordinates, and then of course there's negative versions of those in the negative x direction. So those are all of the possible x coordinates, and then the same thing for the y coordinates, and the same thing for the z coordinates, and the same thing for the w coordinates when we're talking about the entire 120 cell. So if we set up our coordinate systems just right, the formulas for the points for the vertices of this shape are actually very nice. And I got these formulas from Wikipedia, which actually presents an even nicer version of this, where they just list out a very small list of possible coordinates, and then says, oh, well, we have both the plus and minus versions, so that the whole thing winds up being mirror symmetric along the x and the y and the z axes and the w axis as well. And permutations of those, which correspond to other mirroring operations and other symmetries that we wind up having. So there's actually really nice formulas for the coordinates of the 120 cell, which has made this project a lot easier, and it's definitely helped. Wikipedia has, for a whole bunch of different 4 and 3-dimensional shapes, lists of coordinates of their vertices, which has been a huge help in putting together a lot of these 3D models. And in fact, this phenomenon where the coordinates of the Zometool balls wind up being very nice is actually part of an even more general phenomenon that anything that you can build out of Zometool, if you pick your axes correctly, the coordinates of a Zometool ball are going to wind up being a plus b times phi, where again phi is the golden ratio, and a and b are actually integers or integers and a half. So I'll link to a paper on that, but this is essentially based around a lot of the nice properties of phi. For instance, if you have phi squared, that's just going to be phi plus 1, and if you have 1 over phi, that's just going to be phi minus 1. So you can, anytime you have something that's like the golden ratio times bigger or the golden ratio times smaller, it still winds up being of this form, a plus b times phi, where a and b are very nice. So anything that you can build out of Zometool, you can wind up getting nice coordinates for free out of the build, which is just fantastic. So another thing that I wanted to mention about the 120 cell is the fact that, so if we look at our platonic solid models, right, their faces are all on the outside, right? They almost form a sphere, right? We almost have, particularly if you look at the icosahedron, right? We're looking at what is essentially a sphere of faces. The faces of these things are all on the outside. And with the 120 cell, the analog of faces are these dodecahedra. So why do we see so many dodecahedra on the inside of this model? Well, it's not because they're on the inside of the 120 cell, right, in 4 dimensions. They're not on the inside. All of these dodecahedra are on the outside of the 120 cell. It's just that we've projected them down so that they wind up in the center. So, for instance, when we're looking at a projection of the dodecahedron, let's say, what we see is essentially a circle, just like how here what we're seeing is essentially a sphere, and inside that circle there are a bunch of pentagons. But in the actual 3D model, the pentagons are all on the outside. They're all on the outside face. It's only in the projection that they wind up looking like they're in the center. And that's the same thing that's happening with the 120 cell. The 120 cell, all of the dodecahedra are on the outside surface. They form almost a hypersphere in the same way that these pentagons form almost a sphere. It's just that when we do that projection, some of the dodecahedra wind up in the center of the projection. But again, those dodecahedra are actually on the outside. So this is really difficult to visualize, but you should visualize, we have this, this hypersphere, and on the surface of the hypersphere, on the surface, not going inwards any amount, but on the surface, because the surface of a hypersphere is 3-dimensional, we can fit a bunch of dodecahedra. And so it's just a bunch of dodecahedra on forming almost a hypersphere in the same way that these pentagons form almost a sphere. And there's kind of this solid inside, this hypersolid inside, this region on the inside that's being enclosed, that's 4-dimensional, just like how with our dodecahedron, we had pentagons on the outside. They form the surface, almost the surface of a sphere, and then we have a solid inside, which is, in this case, 3-dimensional. That is our dodecahedron. In this case, we have a four-dimensional solid inside to the Hyperdo. So a good way to see this is actually to take a look at cross sections of the 120 cell. So far we've been looking at projections of the 120 cell. We've been just taking all of the points of the 120 cell and ignoring their W coordinates. And what that does is it squishes everything down in the W axes so that it's all in the XYZ space. But what we can actually do is we can take cross sections for particular W values, and we can see what happens when we intersect the Hyperdo with these particular spaces corresponding to particular W values, and we can see how the image changes as we take those cross sections. And so we can see here, and you can play around with this on the Visualizer Interactive. And I've colored each of the 120 dodecahedra a slightly different color so that we can follow them. So let's actually follow this, this blue dodecahedron here. We see that it starts off as a tiny little pentagon, and then the pentagon gets larger and larger, and then it becomes a decagon, and then it turns into a pentagon again, and it gets smaller and smaller, and then eventually it's gone. That's what happens if you take cross sections of a dodecahedron in a particular direction. And you can see various, the various cells are having, we're taking cross sections in different directions, so you'll see different things. Some of these wind up being hexagons as opposed to pentagons. There's various things depending on the angle that you take the cross section at. And then we can see here that it actually switches from blue to orange, and that's what's happening here is that we're switching from taking cross sections of one of the dodecahedra, and then we're switching over to another of the dodecahedra. Right? We're seeing the place where these two faces meet when this switchover happens. Right? We're seeing where the blue and the orange face meet each other. So anyway, the point is that if we actually take half of these cross sections, we can see inside. We can see that these things are in fact hollow. And that kind of makes sense, right? If we take cross sections of a dodecahedron, right, and we're just looking at the faces, right? We're not looking at the inside of the dodecahedron, right? If the inside of the dodecahedron isn't filled, and we take cross sections, we're only going to get, pentagons or decagons or whatever with nothing going on the inside. If we take a sphere and take cross sections of that, right, we're just going to get circles that aren't filled in. If we're looking at the surface of the sphere. And similarly, if we're looking at the surface of the if we're looking at the surface of the 120 cell, that is all of these dodecahedra and none of that four-dimensional space inside, the results is going to be hollow, right? The cross sections are going to be these hollow shapes here. And this is actually, it's very similar to what would happen if you took the cross sections of a hypersphere, right? It would look like spheres that were themselves hollow. So again, just to stress that this shape is in fact hollow, right? The 120 cell is, if we're just looking at the faces on the outside, the faces, the dodecahedra, if we're just looking at those, then the whole thing is hollow. And of course we could fill in the inside, but when we filled in the inside, we would be filling in this four-dimensional space with four-dimensional volume. All of these dodecahedra are on the surface of this hypersphere. It's just that due to the projection, a lot of them wind up getting projected to the inside of this particular model. And along those lines, this these dodecahedra are positioned in a regular way. So, for instance, if we're talking about a platonic solid here, saying that this solid is regular means that if we take any face and any other face, we can rotate the icosahedron to put that other face where the other to put the one face where the other face was, and the icosahedron will look the same. That is, that those two faces are essentially the same face, and we can also rotate the faces however we want, and the icosahedron will stay the same. So not only are all of the faces essentially the same, but we can also rotate all of the faces however we want, and we'll still wind up getting the same shape. There's nothing special about any of the faces, and there's no special orientation to any of the faces, which again is difficult to wrap our heads around for this 120 cell, right? The idea that none of these dodecahedra is special. It runs a bit counter to the fact that we have these central dodecahedra in our model, but the only reason that those dodecahedra are special in the model is because of the projection that we chose. All of the dodecahedra wind up being essentially the same. That is, we can rotate the 120 cell in 4 dimensions. We can choose different projections, and that will take any one dodecahedron and rotate it into the place of any other dodecahedron that we want. And of course, we can rotate the model to rotate the dodecahedra however we want. So this is really hard to imagine, but again, if we think about, we have this surface of a 4-dimensional sphere, and all of the dodecahedra are positioned regularly around that surface, so that, again, we can rotate, just by rotating, we can move any one dodecahedron to the position of another dodecahedron as we want. So that's about it for what I wanted to say about this particular model. It is one of many platonic solids in 4 dimensions. There are in fact 6 platonic solids. We get one more than we get in 3 dimensions. Things get a little bit boring after that in dimensions 5 and higher, so 5, 6, 7, and so on and so forth. It turns out that there are actually only 3 in each dimension. Platonic solids. The interesting stuff all happens in 3 and 4 dimensions. But I hope that this video was able to give you some intuition for 4-dimensional platonic solids, and in particular the 120 cell, the geometry of this 4-dimensional and therefore very difficult to visualize shape. And I hope to see you in a future video.